Hello, hello. How are you guys today? Okay. So we'll finish with part two of the diels-alder practice problems we started last night, with the last three practice problems, and then we can move on to another topic. So let me pull those questions up. Hey, Madison. So let's do that. Copy. Oh no, I think we did that one last night. So let's do this one. And the other two. This one. And this one. Okay, I'm also gonna copy and paste over the process that I gave you guys last night, the 3-step process to do when we approach these diels-alder problems, so we could reference it when we do these problems. The last two are gonna be, in my opinion, like the more confusing ones because they could give you multiple products, like more than 2 products, like 4 products. Okay, so let's get started with the first one here. The first one is going to have this problem where the first step is to identify where my diene and dienophile is. This yellow highlighted part of the molecule here is the diene. This is the dienophile right there. And it's in the orientation where we are usually like used to seeing it in, where the diene is this way and the dienophile is this way. Then once I found that, then I look at the regioselectivity where I have to align the charges, right? So I have 2 EDGs on the diene. But this EDG right here is a stronger EDG because it could directly donate electrons into the system by resonance. Whereas this R group here is a weaker EDG because it's only donating electrons by induction. There's no pairs of electrons for this R group to donate directly into the system. So when we think about the resonance structure, there's going to be a partial negative charge on this carbon right here. Like a full negative charge on the resonance structure, but the overall structure, this carbon here will have the negative charge on the diene. And we see that this is the EWG right here, and it's an EWG by resonance because it's directly withdrawing electrons from this dienophile system, giving this carbon here a positive charge. So when we draw the pocket between the diene and dienophile, the charges do align, so we don't have to do any flipping, rotating, or anything. We can keep it like that and proceed with the mechanism, right? So if I number this 1, 2, 3, 4, 5, 6, and I proceed with the diels-alder mechanism, which are these 3 electrocyclic arrows there, I would get this product here, which is my product always for diels-alder, that cyclohexene, right? Where this is 1, 2, 3, 4, 5, 6. And we could track where the double bonds are going to. The double bond between 5 and 6 made that new bond between 4 and 5. The double bond between 3 and 4 made that double bond between 2 and 3. The double bond between 1 and 2 made this new bond between 1 and 6. So that's how you can keep track of everything. Now, let's talk about the stereoselectivity. This right here is an out group because it's facing outside of the pocket. This right here is the in group because it's inside of the pocket between the diene and dienophile. And this right here is our EWG. And based on the Endo rule, the out group is going to be cis to the EWG. So if I draw out my out group as a dash like that, that means that my EWG would also have to be a dash to follow the endo rule, right? And this methyl group here on carbon 1 is trans to the EWG. So because this EWG is a dash, this in group methyl group here has to be a wedge, trans to the EWG based on the endo rule. And we can do plus minus here because everything could have been flipped in this case, right? So that's the major product for this diels-alder problem here. Any questions on this before I move on to the next one? Okay. Let's move on to the next one, which is this one right here. Let's do the same process. First step, identify the diene and dienophile. This is our diene. This is our dienophile. So the way that it's drawn is weird, right? Because we're not used to seeing the diene this way. So I'm going to rotate it in the way that we are used to seeing, which is that dienophile that way and the dienophile this way, like that. Where this part right here is the diene, this part right here is the dienophile. And let's number this. Let's say this is 1, 2, 3, 4. That's going to be this 1, 2, 3, 4. And let's say this is 5 and 6. 5 and 6. We see that 3 and 4 has that fused cyclopentene ring, which I'm going to draw out like that. Right? Everything else is decoration. Find the diene and everything else would be decoration. Just copy and paste whatever that is. And then 5 and 6 has this aldehyde here, which are the EWGs. Now the charges here align because this dienophile has partial positive charges on both carbons, since there's 2 EWGs on both carbons, so it doesn't matter here, right? Now when we do the mechanism, we're gonna get this product here. Let's draw out the cyclohexene base product template like that. And let's draw out the pocket between the diene and dienophile. This group here on 4 is considered the out group because it's outside of the pocket, which means that it's going to be trans to the EWGs, right? And the EWGs, let's say that they are dashes. If there are dashes, then that out group on carbon 4 would also have to be a dash to follow the endo rule. But be careful here. This carbon 3 right here is still sp2 hybridized. So the bond there is still going to be flat and planar. This bond here does not become a wedge or dash. It stays flat and planar because of that sp2 flat carbon right there, right? And in this case, the dienophile has 2 groups, which can be cis or trans. Right now, these 2 groups are cis to each other. So we got to maintain that cis configuration, right? Which is this third part of the process here. Maintain dienophile configuration, right? Now the next one is going to talk about the trans dienophile, which is going to give you 4 different products here, right? This one here gives you 2 different products, that and its enantiomer. But now let's look at the last problem here. By diels-alder. Okay, so this is our diene. This is our dienophile. Here are our EDGs, and here are our EWGs. So in this case, we don't have to worry about the regioselectivity again because both carbons of the dienophile here have partial positive charge because they have 2 of the same EWGs on them, right? So we could proceed with the same mechanism and draw out our template product, right? And now this regioselectivity endo rule, let's draw that pocket between the diene and dienophile where the new bond is going to be formed at, like that. This right here is our out group. This right here is our in group. And notice how when I classify the out and in groups, they're always going to be on the outside carbons of the diene, which I number them as 1 and 4 in the way that I number them, right? You don't have to number like that, but the way that I number them, these outside carbons are carbons 1 and 4. So that's where the out and in groups are. right? This is not an out or in group right here. That's a group on carbon 2. These are EWGs. Now, based on the endo rule, the out group is cis to the EWG. But we have two EWGs right here, and they're trans to each other. So how do we choose which EWG to make this out group trans to? It's going to be both, right? So let's focus on this top one to follow the endo rule. So let's say that that EWG is a dash that forces the other EWG to become a trans, right? Because these two CNs here are trans to each other, and we have to maintain that trans configuration. But we're choosing the top CN to follow the endo rule, so that there's going to be dash with the ethyl group because it's an out group. And the methyl group on that carbon is a wedge because an in group is trans to the EWG, like that, plus minus. So that's one set of the products. The other set of the products would be if we chose the bottom CN to follow the endo rule and a top CN to not follow the endo rule, like that, right? And these are two different diastereomers of each other, right? Because we noticed that this car center did not change, right? Whereas these car centers here did change, right? So that's why they're diastereomers of each other. And that's why following the dienophile configuration is the hardest one, because we get 4 different products here, right? This is the trans CN, and we got that trans CN because of this trans dienophile here, right? And the reason why we get different ones is because both of these CNs here could follow the endo rule. The product on the left, that CN follows the endo rule. The product on the right, that CN follows the endo rule. Would there be another methyl? Yes, there would be another methyl on carbon 2 right here. And this methyl here has no wedge, no dash. It stays as a flat and planar carbon because this carbon right here, carbon 2, is sp2 hybridized, and it stays sp2 hybridized, making it flat and planar, no wedge, no dash. Yeah, so don't forget about those groups as well on the sides of the, on the inside of the diene, like that. Right? Yeah. Okay, so that is the diels-alder predicted product balance for the AATC Edna Lamson worksheets. I will do practice with Maria Jones, Levens, and then the Helix official ones after. But in my opinion, the diels-alder reaction here is going to be the hardest reaction to master for the next midterm, right? Electrocyclic reactions are more doable, and the benzene reactions are definitely more doable for the next midterm. Okay. Wiley, Madison, did you guys want to go over a reaction for 128B or 8B?
If there's time, I have a couple questions on like the lab reaction mechanism. We haven't quite like gone over it, I don't think quite yet. So I was just wondering how to do that, but if anyone obviously else, I don't want to take up too much time.
Right. I think we do have time. You can send me the lab problem through text or here on the Zoom chat. But let me find my phone first.
I think I dropped it in the Zoom chat.
In the Zoom chat?
I'm not sure
okay,
if it's,
let me see.
You can see it though. Just let me know.
Oh, I see it. Yes, I see it. Okay. Got it. Open. Okay. Lab. Post-lab questions. Okay. Write the detailed reaction mechanism for the following reactions. So A has this molecule reacting with these reagents. Let's focus on this right here. In lecture, do you remember the name aldol condensation, aldol dehydration?
No.
No, okay. It's okay. We'll go over that here.
Oh gosh, okay.
So we have what functional group here do you see in the reactant molecule? What is the functional group we see here?
Aldehyde?
Yes, an aldehyde. And what kind of reagent do we have? What set of reagents do we have here? When you see NaOH, H2O, and heat.
Um, like their dehydration, like they're sucking, like the heat's gonna like, I'm
Yep.
thinking about this like lab wise, like it's gonna take away from the product.
Yeah, right. They're gonna dehydrate something. They're gonna take away water, right? But NaOH, OH minus is a base, so we are in basic conditions here, right? Because whenever you see Na that is positively charged, that means that this OH here is negatively charged. So our
Right.
hydroxide ion, OH minus, is our base, our strong base here. And when we have a strong base, we're gonna look for an acid-base reaction. Right? We're gonna look for the most acidic hydrogen in this molecule here.
Okay.
The aldehyde hydrogen here, we never want to deprotonate that. We would never want to grab that hydrogen, right? That's not acidic. But when you see a ketone or aldehyde with no other functional group, right? No alcohol, no carboxylic acid, the most acidic hydrogen is the alpha hydrogen. Have you heard of the alpha hydrogen or the alpha position before?
Yes.
Yes. Where would that be here? Where's the alpha carbon and alpha hydrogen here?
It's relative, is it relative to the oxygen double bond to
Yes,
the
but there's
carbon?
two atoms. Yeah, the carbon, neocarbon. It's relative to the carbon, neocarbon. Right.
Okay.
Mhm.
So the alpha is the closest and then beta
Uh-huh.
is the second closest.
Right. Because this dot here is the carbonyl carbon. The alpha carbon is the closest or the first atom away from the carbonyl carbon, and the beta carbon is the second atom away from the carbonyl carbon. And you can keep
Right.
going like gamma, delta, epsilon. But that's how we like position the carbons relative to the carbonyl carbon. Right. So this alpha carbon here has two alpha hydrogens, but I'm gonna draw out only one of the alpha hydrogens like that. Right, so this right
Okay.
here is one of our alpha hydrogens. We have two alpha hydrogens, but I'm going to draw out one of them for the mechanism. This OH minus here is going to grab that alpha hydrogen, and the bond here between the alpha hydrogen and alpha carbon is going to break away to make a double bond right there. But that's going to break the octet rule for this carbon here, the carbonyl carbon, because it's going to have 5 bonds when we make a double bond right there. 1, 2, 3, 4, 5. To conserve
Mm-hmm.
the octet rule, we have to pop one of the bonds of the double bond onto the oxygen like that.
Okay.
Right? And this is showing the movement of the 2 electrons here of that bond to that oxygen to give us this intermediate of the mechanism right here. And before, this oxygen here had 2 pairs of electrons, but they're invisible. 1, 2. Now it has 3 pairs of electrons. It gained a set of electrons, a pair of electrons, from this bond right here. This bond had 2 electrons, which moved onto this oxygen, giving it an extra pair of electrons.
Okay.
Right? And the formal charge of that oxygen with 3 pairs of electrons and a single bond is negative charge, like that. Right? Okay, so our side product here, if this is mechanism, would be water. We formed water here. Because this OH minus grabbed the H, forming H2O, neutral water.
Okay.
Now, this next step here, right, we formed a negative charge. And it looks like the oxygen is the nucleophile, but this is the confusing part. That O minus there, because it is next to this alkene right here, this is what we call an enolate ion. Right? Because an enol is when we have an alkene next to a neutral alcohol. That is an enol. When you see enolate, think of an ion, something that has a charge, right? And specifically, this enolate ion will have a negative charge
Okay.
on the oxygen. And think of it as a deprotonated enol, right? Like if we were to introduce an acid to the enol and deprotonate the alcohol, then we would get an enolate ion, right? Where the oxygen lost its hydrogen and gains a negative charge. That's the deprotonated enol.
Okay.
Now, this O minus here, the oxygen is not the nucleophile or base, right? The reason why is because I'm going to draw you out the resonance structure just to make it more clear. We could push one of the pairs of electrons on oxygen to make a double bond right here, reforming the carbonyl, carbon double bond oxygen. But that's going to break the octet rule, again, for this carbon. right? Because that's gonna have 1, 2, 3, 4, 5 carbons, bonds, I mean.
Right.
But to conserve the octet rule, we're gonna push this double bond onto that carbon right there, giving that carbon a pair of electrons and a negative charge. Right? So I'm gonna draw the resonance structure going down here like this. Right? And resonance structures, we gotta maintain the charge. Since we had a negative charge here, we gotta make sure that we have a negative charge in the resonance structure as well, which we do have on that carbon right there. Right? Now, which resonance structure would you say is the major contributor? Which one looks more stable to you? Is this resonance structure or is this resonance structure right here? Which one looks more stable?
The one on the bottom.
So the one, what's the difference between the one on the top and the one on the bottom? Like what's the difference between them that you see? Like what's the difference?
That carbon is, well, the carbon is unstable, but the oxygen's more stable, right?
Yes. So the carbon here with the negative charge is more unstable with the negative charge because oxygen is more electronegative than carbon, so it can hold that negative charge better. So our major resonance contributor is the top one, right? Because the top one is more stable with the negative charge. Our minor resonance structure is the bottom one because the negative charge is less stable on that carbon right there, right? And Peyton and Wiley, this is what you're going to be learning at the end of the quarter. Wiley is learning that right now. Peyton is this is one of the many reactions you heard about at the end of 118B. So this is actually pretty good alignment with all the courses here. Yeah, this is like the difficult stuff, the inulate chemistry. There's a lot of reactions with this guy, this little guy right here.
Really?
Yeah.
He's not very happy.
He's not very happy. Yes.
Are these reversible too?
Reversible up until a certain point.
Okay.
Right? But overall, it's an irreversible reaction.
Okay.
Right now, we're still in the irreversible step. Okay.
Okay.
Now, because this is the minor resonance contributor, it is unhappy, less happy, more reactive. Right? This one is major, it's more happy, less reactive. So that's why I'm gonna star this alpha carbon right here. Right? This is the carbonyl carbon, this is the alpha carbon. That alpha carbon is my nucleophile and base, like that. Right? Which is gonna attack some electrophile. Or electrophile. Or electrophile or base. Or acid, acid, H plus ion. Right? And this is the common nucleophile for a lot of these reactions, right? Like, there's a lot of reactions that can happen with that. Okay, one of the reactions is aldol condensation. So we don't have to actually draw out this resonance structure here. I'm just going to redraw the enolate ion that we formed originally, which is this right here. But I know that my nucleophile is this alpha carbon here of the double bond. I'm going to bring in another aldehyde because we have excess amount of aldehyde floating around. This dot carbon here, because it's partial positive charge, is my electrophile. This dark carbon here is my nucleophile. Right, not this O minus, and we know why already because of the resonance structure. Like, resonance structure puts a negative charge on that alpha carbon, making it more reactive, more unstable. Right, now to draw the mechanism here, we're gonna reform the carbonyl and have this dark carbon attack the dot carbon, and we're gonna try to make a new bond between the star and dot carbon. Right, but this dot carbon is gonna have 5 bonds if we do that without doing anything else. So to conserve the octet rule, pop that double bond onto the oxygen, and this is why I star and dot things, to keep track of the atoms, right? So this molecule here is going to be my starred molecule. This right here is my new bond that I formed between the star and dot molecule, right? That new bond comes from this attack right here. And this dot carbon here is attached to an ethyl group, CH2CH3, CH2CH3, a hydrogen, but I'm going to leave that as invisible somewhere here, like that, invisible. And it was bonded to a double bond oxygen, right? It was double bonded to an oxygen, but it's now a single bond O minus, a negative charge because it gained a pair of electrons from that electron push right there, right? Like, if we do the same thing, before it had 2 pairs of electrons, but now it has 3 pairs of electrons, it gained another pair of electrons from this bond right here, the 2 electrons of that bond, popping onto that oxygen, right? Making it negatively charged, like that.
Oh, okay.
Yeah. What? Yeah. Does it make sense so far on how we got this structure here?
Yeah.
Yeah, right. That's like this is probably the most confusing part, connecting these two pieces together, but the star and dot technique will definitely help you out with that.
Yeah, that it does help.
Uh-huh. Right. Because like if we track things like this yellow molecule here, if I highlight it in yellow, is this yellow molecule here. Right. This blue molecule here is this blue molecule here with this invisible hydrogen. I didn't draw out the hydrogen.
Hmm.
This new bond in red right there is this arrow right there connecting those two pieces together. Connecting the star and dot together like that. Right. Okay. Now, what we're gonna do is we're gonna protonate the O- to make it a neutral OH. And our proton source we have here, be careful, it's not H2O plus acid or H2SO4. The proton source, the acid is H2O, water. Right? So I'm gonna draw out the water like this. Just to show that this O- is going to grab that hydrogen of the water, and the bond between the hydrogen being grabbed and oxygen is gonna pop off onto the oxygen like that, creating OH minus side product. Right? So this is still reversible here. Neutral OH. Now, when you do practice problems with this, the answer might look different, but it's gonna be the same thing. It's just oriented differently, drawn differently. But
Okay.
I'm just gonna draw you it this way, which is not the most aesthetic way to draw it. Like the
Uh-huh.
key, like Levens is probably gonna give you the most aesthetic way to draw it with the like longest bond line form and the horizontal line like that. But it's gonna still be the same thing like this, you know?
Okay.
Right. Okay. So now, once we have this right here, I'm just gonna show you what our final product is gonna be like. So this is the carbon right here.
Hmm.
This is the alpha carbon right here. And this is the beta carbon right here. And I'm interested in this beta carbon specifically, not this beta carbon, because this beta carbon here has the alcohol right there.
Right.
Right? Our final product, we want to get rid of that alcohol and put a double bond between the alpha and beta carbon, like that.
Oh, okay.
Right? So I'm just gonna draw out the product for you, just for predictive product sake, like to save time. And I'm gonna show you the
Uh-huh.
mechanism afterwards.
Okay.
But this is gonna help us determine what the next steps are. Right? And this right here, since this is the carbonyl-carbon, this is the alpha carbon, this is the beta carbon, you might see this as an alpha beta unsaturated carbonyl. It's a long name, but what it means that is that this is our carbonyl here, our carbon double bond oxygen. This is our alpha carbon right here, the first carbon away. This is the beta carbon here, the second carbon away from the carbonyl-carbon. Because
Hmm.
there's a double bond there between the alpha and beta carbon, that double bond is considered an unsaturation. Like when you take biochem, you're gonna see like an unsaturated fat or it's versus a saturated fat. An unsaturated fat is like when you have a double bond, a pi bond, like that.
Right. Okay.
Right? Which is why this is called an alpha beta unsaturated carbonyl, like that. Okay. Now let's move on with the mechanism here. Because we have heat, we're gonna do the irreversible step now. This point here of the mechanism is our irreversible step. Now this last step here is kind of like a boomerang. Right? I'm gonna draw out the alpha hydrogen, which is the most actually yeah, for this mechanism, that's the alpha hydrogen right there. An OH minus is gonna float around, grab that alpha hydrogen, form an enolate ion. Wait, this right here is still reversible actually. Like we're still reversible here. Boom. O minus H, because this enolate ion can actually go back to the carbonyl form. Right there, like that. Okay. Any questions on this before I move on to the next step? Like how I got from here to here?
No, that makes sense.
Uh-huh. Okay. Now, once I have that, this is the irreversible step now. So I'm just gonna draw an arrow going from
Hmm.
here to the final answer, final product. With no reversible arrow, right? This is like an irreversible arrow right here.
Right.
This O minus here is gonna go down to form a carbonyl, carbon double bond oxygen. Shift this double bond over to make a double bond over there, and then kick out that OH group. Right?
Shift this over here and then you kick out. Oh, okay.
This first arrow here makes the double bond between the carbon and oxygen, makes the carbonyl.
Mm-hmm.
This double bond here shifting over makes a double bond between the alpha and beta carbon. That's our alpha beta unsaturation right there.
Right.
and that kicks out the OH right there. That's why we don't get an OH anymore, right? And we're used to seeing this OH as a bad leaving group, right? But because of heat and enough energy, we're able to do that and kick out the OH minus, which is already floating around in the solution as well, because we're in basic conditions. There's other OH minuses around, kind of stabilizing it, right? But the main reason is because of heat here.
Right.
Heat, right? And the reason why it's irreversible is because wait, actually, because I can see this OH minus coming here, attacking that. Boom, boom. Like that. Giving us this thing again. Right. Yeah. So this point here is the irreversible step right here. Irreversible step. Right.
Okay.
Okay. Let's see. OH minus. Heat. Yeah. Okay. So that is the final answer right there, like that. With all the step-by-step mechanisms of the arrow resin structures, if you want to draw them, and like techniques on how to connect the pieces together, alpha beta carbon, like that. Okay.
Yeah.
Yeah.
Okay. Perfect. Thank you so much.
Yes, of course. I would practice that with part B.
Okay.
Right? But I'm gonna give you a hint here. Part B, we have a ketone, which is acetone, and a benzaldehyde, two equivalent of benzaldehyde. And there is a way to predict the product quickly without having drawn the whole mechanism, because you saw how it was like so long, the arrows and everything. To save time on the quiz, if this was a predicted product problem, I'm gonna show you a way how to do it quickly without doing the whole mechanism.
Okay.
Okay. But here's the hint of this one here. These two alpha carbons here of the ketone are gonna be the nucleophiles, and because we have two benzaldehydes, I'm just gonna draw them out like this. Our two electrophiles are gonna be the two carbonyls of the two benzaldehydes we have, like that.
Okay.
Right. So for the first reaction, deprotonate this alpha hydrogen to make that negative charge attack the first equivalent. Proceed with the whole mechanism that we just did, and then that's your halfway point. And then you have another hydrogen here to deprotonate, make that the negative charge, attack the other benzaldehyde, and give you another final product right there. Right. So we're doing basically the reaction we just did 2 times. 1 time for this alpha carbon attacking that carbon, and another time using that alpha carbon attacking that carbon right there. But it's gonna be the same mechanism we just did 2 times. Right. Okay, so try that out and then tell me what you get later on.
Okay, and so you're supposed to have 2 products, like 2 ending products?
We're gonna get 1 big product, right? Because ignore this other benzaldehyde right here. If we deprotonate this alpha carbon right here, giving this alpha carbon a negative charge and attack that carbon, pop the bonds with oxygen, and then a lot of steps that we just did, we're gonna get the intermediate right here, which is gonna look like this, something like that, right? With the alpha hydrogen right here. We're gonna deprotonate that alpha hydrogen on the other side to now attack the second one that we ignored earlier, right? And then our final product is gonna look like this, right? And then that other part is gonna look like a benzene, like that. So wait, so this right here is gonna actually be your product right here. But I want you to draw the mechanism of how we do that. I'll show you how to think about that, like without doing the whole mechanism.
Okay.
Yeah, how to do this, because that's gonna definitely save a lot of time for sure.
Okay, awesome.
Yeah.
Thank you so much. I'll try that.
Yeah, of course, Madison. How did the quiz go, by the way, last week for you?
It was better. It was
better?
I got a point more than my best score so far. So
okay. Yeah. One quiz gets dropped, right?
Huh?
Like does one quiz get dropped for her class?
Yeah, I already definitely have my drop quiz, but my grade didn't go down. I felt fine about it. So as long as it's not too detrimental, then we're fine.
Yeah, that's good. That's good.
But the average was a 35 or
35 out of 60.
67.
67. Oh,
yeah.
39 out of 67. That's like 50, 60%, something like that.
Yeah, like the ab. and then the lowest was like a 5 or something.
Yes,
So
average for leave-ins.
yeah, it wasn't too great. A lot of people did not finish. I don't think
Yeah, I
people
heard.
finished at all.
Right.
You heard.
Yeah. Oh
But I
my
mean, it is
gosh.
what it is, so we'll see.
Yeah. But it's so fast, like every 2 week quizzes. And it's like her quizzes is
Yeah,
like the midterms.
it
I've
stresses
seen
me
it.
out,
Yeah. Oh my
but you gotta
gosh.
get it done, so there's
Because
no
you
other
know
option.
it, but then the time just like makes you like lose points, which is not like very representative of what you do
Yeah,
know. Yeah.
100%.
Mhm.
Thank you. I'm gonna probably log off and try this, and maybe I'll send you a picture of it.
Okay, yeah, of course, of course. Yeah. Yeah. See you, Madison.
I have a good one.
You too. Good night. Okay. Hey Jenna. Madison just left, but she was also from 8B, and then this was the post-lab question, part A, part B, and this is about aldol dehydration condensation. Are you familiar with that reaction, Jenna?
No, actually, I need to do that. Oh, I was stuck on that. But
Okay.
it's okay. I can watch
The
the
recording.
yeah,
Yeah,
yeah.
I
I don't have to
definitely
go over it
explained
again.
everything like in depth, step by step, charge by charge, arrow by arrow, alpha beta carbon by alpha beta carbon. So that recording will definitely help you. And I send this here.
Okay.
Uh-huh.
Was
Okay.
this from, I can't remember. Did she say it was from this week's lab or last week's?
Oh, I don't know. She didn't tell me, but she
Okay,
said
okay.
the thing. It is lab uh 6 VI on dibenzoylacetone.
Oh, okay, that was last week. Yeah,
So,
that because it's due tonight.
oh, it's due tonight, the post lab.
Yeah.
Oh, wait, so wait, and you didn't know how to do this? You just did you finish this
Low
then?
key, I've been slacking on labs because there's already so much in lecture that
Uh-huh.
like I kind of forget about lab, but
Okay, okay. So this was the first problem here. This is the answer, the mechanism, and the product. Do you want me to go over the mechanism for this one here, and the product as well, or do you
wait,
already have it?
is this also lab?
Yes, this is also lab
Wait,
1B.
let me check.
Yeah. Wiley, does this look familiar of what you're learning right now in class 128B with the enolate chemistry?
Not that in depth.
Not yet, right?
We just started
You just
aldehydes
started.
and ketones, yeah.
What about geminal
Oh, okay.
diols, hemiacetal acetals?
I
Do
think we're
those?
learning that soon.
Okay, okay. Alpha carbon, acidity?
Alpha carbon. No, but
No.
in mass spectrometry we learn alpha cleavage.
Okay, okay, okay. Oh, you're learning the spectroscopy stuff before the
Oh no, we
reactions.
already finished spectroscopy. We're doing alpha.
Oh, okay, okay. Uh, I see. What is the last thing you're learning about? Like what topic for the aldehyde ketone?
I have no idea.
Okay, okay. Nomenclature or something like that. Okay.
We just did a little bit of nomenclature.
Okay, okay. I see. Yeah. So this right here is what you're gonna be seeing very soon. Yeah. And Peyton too for 118B. After midterm 3. This is post midterm 3 though. After the benzene stuff. Okay.
We can go over this actually because I was stuck on that.
Yes. Okay. Let me see the vocab questions so that I can use those terms when I explain this for Levens class. This overreaction 1A is an reaction. The reaction first forms an anion which undergoes a mechanism. Then with heating, the intermediate goes undergo a reaction to form the final product. Condensation, dehydration. Okay, yeah. So that's good. All these blanks right here, I said when I was explaining the mechanism to Madison earlier. But I'll redo that for you again here. But let's start off with a simple reaction.
Okay.
So it's gonna be very similar to what I just did, but let's say we have an aldehyde in excess. Like this. This is right here is actually gonna be the exact same thing then. And we have base, NaOH, water, solvent, and heat. We see that we have a strong base, OH minus right here. So we're gonna look for the most acidic hydrogen on this aldehyde molecule. If there's no other like group like carboxylic acid, then our most acidic hydrogen is the alpha hydrogen. So this is the carbonyl-carbon. The alpha carbon is the first carbon away from the carbonyl-carbon. This is the beta carbon, the second carbon away from the carbonyl-carbon. And you can keep going on, right? Like if there's more carbons, you could say there's a gamma carbon, delta carbon, and epsilon carbon. So this is the alpha hydrogen right here. The reason why this alpha hydrogen is more acidic than this beta hydrogen is because its conjugate base is more stable, right? So let's say, for example, we grab that alpha hydrogen, the bond between the alpha hydrogen and carbon makes a double bond right there, which pushes this double bond onto the oxygen like that, giving me this intermediate right here. Right? Before, this carbonyl oxygen had 2 pairs of electrons, but now it has 3 pairs of electrons. It gained a pair of electrons from this bond here. Those 2 electrons popped onto the oxygen, giving it a negative charge, a 3rd pair of electrons. Right? And we see that this conjugate base here is relatively stable because it can do resonance. Right? This O- here can actually go down and let me actually draw that out like this. It could actually go down, form the carbonyl again, and push this double bond onto the carbon, giving us this resonance structure right here. Okay, now that's why this alpha hydrogen here is the most acidic, right? Because if we were to, let's say, deprotonate the beta hydrogen, like let's say we grab that beta hydrogen and give this carbon here a negative charge, we would get that negative charge on the carbon that is unable to do resonance because of this sp3 roadblock, blocking resonance. Right, so this negative charge here is very angry, not very happy. That's why that is not as acidic, like this beta hydrogen here is not as acidic as this alpha hydrogen right there. We want to form the more stable conjugate base, which is this one here that can do resonance. Okay, so ignore this and the left right there. Now, which one would you say is the major resonance structure? The one on the top or the one on the bottom? Which one looks more stable for you?
The bottom one.
And why would you say that? What factor would makes that more stable?
The double bond. So it has
Oh, you're thinking about the double bond strength. Like, yes, this carbon double bond oxygen is stronger than that carbon double bond carbon, right? That is a stronger bond, right there. Right. But when we think about this, think about the charge. Yes, the formal charge. Where is the formal charge more stable at? The more electronegative oxygen atom or the less electronegative carbon atom?
Oh, I didn't see that. The more electronegative oxygen.
Yes, the more electronegative oxygen atom has an easier time holding that negative charge, so that's the major resonance contributor. This is the minor resonance contributor. Yeah. So, yeah, thanks for letting me know that you were thinking about the double bond strength for the major resonance structure, but the charge here would actually be the bigger factor compared to the bond strength, right? The formal charge stability. Okay, so it's good to know that that's a misconception right there, because I also asked Madison earlier too, and she also said the bottom one as well.
Yeah.
Okay. Right now, this minor one right here is more reactive because it's angry, right? It's more reactive. Whereas this one right here is less reactive because it is happy and it doesn't want to react with anything. Which is why this O minus here is not our nucleophile or base. Not our nucleophile or base. If we put some kind of electrophile or acid floating around, this O minus here would not get protonated. It will not attack an electrophile. What will act as a nucleophile or base is this stored alpha carbon right here. Like that, right? This alpha carbon is our nucleophile or base. Nucleophile or base. Okay? Now, we don't have to draw out this resonance structure. Maybe for Levens you do, because Levens loves those resonance structures for the mechanism, but we can just draw it from this enolate ion that we formed in the first place. And I want to show you this difference between them, because I always got confused on like why the professors draw it in like this way rather than this way, because it's easier to see where the nucleophile is at in this form, right? Like it's easy to see the negative charge on that alpha carbon, like that, right? But the reason why professors draw it in this form is because this is the major resonance structure. Like it exists more in this form over this form right here, right? But the reactive thing here is this alpha carbon right there. So I'm gonna draw in another aldehyde here because we have excess amount of it. This carbon to carbon here is our electrophile because it is partial positively charged. Now you could use either resonance structure to proceed with the mechanism. Professors usually proceed with the first resonance structure because that's the major one that exists in nature, more likely. So one pair of electrons is going to go down to reform the carbon double bond oxygen carbonyl, and we know that eventually this alpha carbon is going to have a negative charge, which is going to attack the electrophile, put the double bond to oxygen to give us our intermediate here. And the reason why I star and dot my atoms is because that allows me to connect the pieces easily. This is my starred atom. This is the new bond between the star and dot atom right there, right? Like if I highlight this molecule here in yellow, that yellow highlighted molecule is this yellow highlighted molecule right there. If I highlight this blue molecule right here, where is it? Right here, in blue, with the dot, I didn't draw that out yet, right? But this right here is the new bond between the star and dot from this attack right here, right? And now we just draw whatever is attached to the dot. We copy and paste everything, the decorations. The dot is attached to an ethyl group, 1, 2, a hydrogen, but I'm going to leave that as invisible. And it was double bonded to an oxygen, but it's now single bonded to an O minus. So that's the blue molecule right there with the invisible hydrogen that I didn't draw out. And this red arrow right here where the star attacked the dot is this new bond right there between the star and dot.
Oh. Okay, that makes sense.
Yeah, so that's how we can connect the pieces, which is probably the hardest part of the mechanism, right? Like how I connect this and this together from that attack. Because some people add an extra carbon by accident, they just start guessing or lose a carbon by accident like that. But if you star and dot it, like that helps you keep track of everything.
Numbering it too is helpful.
Yeah, you could also number it as well. Like you could say this is like 1, 2, 3, 4, or you can even letter it like A, B, C, D. But make sure it's consistent and you don't lose your numbering system or your lettering system.
Yeah.
Numbering system is like especially useful for intramolecular reactions when you form rings, you know, like when from your nucleophile to electrophile, whether you form 5, 6, or 7 membered ring. Yeah. Okay. Now, it's much easier to draw this arrow right here, right, from the alpha carbon attacking the carbon and pushing the ones to oxygen. That would give us the same thing right here, right? Because we can directly see where the nucleophile is at, which is this alpha carbon right there. So, and when I took the class, I always drew out the nucleophile in this form right here, right? But most professors draw in this form. It's the same thing. They'll give you the same product, but the reason why is because this is the major resonance structure that exists more in nature. Like that would actually attack this thing right here, right? But Levens should accept both. Like if you draw out the resonance structure, you could use either or resonance structure to attack the electrophile right there, because it's still the same nucleophile, the alpha carbon right there, right? It's just that this one is easier to see why this is the nucleophile, because it has that full negative charge. This one is harder to see because the O minus has the negative charge, so a lot of people would use the O minus to attack the carbon, but that's not the case because we said earlier that this O minus is happy, less reactive. It's this alpha carbon here that's the nucleophile, and that's hidden in this resonance structure because we don't see that full negative charge on that alpha carbon, right? But just know in the back of your mind that when you see this enolate ion here, right, which is part of the vocab question, this is an enolate ion. The O minus is not the nucleophile or base, it's this alpha carbon right here. Right. And for you to remember what the enolate ion is, this is the enol, an alkene next to an alcohol. An enolate ion is basically a deprotonated version of the enol, right? Like we take away hydrogen and give the oxygen a negative charge. That's an enolate ion, like that. Okay?
Oh.
Yeah.
Wait, so back to the part before.
Yeah.
Are you saying maybe I just didn't I didn't hear, but
yeah.
I was thinking that because the second resonance structure is more reactive, then we could like attack that here. But what did you say again? Why that wouldn't work?
Oh, this would work. You could use this. This is also good. You could do that.
Oh, okay.
Right. Which is what I did when I took the class. Because it looks more easy, like to see where the nucleophile is at, right? Like this alpha carbon here has that full negative charge, right there.
Yeah.
So it's easier to see why that's the nucleophile. right?
Yeah.
What I'm saying is that professors don't usually draw in this form. They usually draw in this
Yeah.
form and then draw the carbonyl reformic and then having that alpha carbon attack, which is sneaky, right? Because we don't see the negative charge here. Like, where's the negative charge there, right? We actually have to think about the resonance structure behind the scenes, which is that right there.
Okay, so you can't show it going from that carbon that you're pointing at right now.
This one here, we can, right? We can do that, like, which is the mechanism, but we also have to push this down here, right? Like, this oxygen minus here has to go down, and we know that this is going to break the octet rule for this carbon, because when we do that, this is going to have 1, 2, 3, 4, 5 bonds. To conserve the octet rule, this bond here has to go to that carbon, giving it a negative charge, right? But instead of drawing that resonance structure out, we could just directly use that negative charge to attack the electrophile here right away. Like that.
Okay.
Yeah.
So both still work. The
both
first
still
one, you
works.
just have to show the process of it.
Yes, that's right.
Okay.
And that is what I wish professors talk about, right? When they do this mechanism, because they just do it, but like, it's kind of misleading because we see a full negative charge on the O minus, which looks like the nucleophile, which looks like the one that should be attacking the electrophile right there.
Yeah.
But it's not, because this is an enolate ion, and when you see an enolate ion, the nucleophile is always the alpha carbon, right?
Okay.
Because the negative charge on the alpha carbon is less stable, more angry than the negative charge on the oxygen. Right.
Okay.
Yeah.
Is that all there is for that question?
No. We're not done yet. We're not done yet. Yes, we're not done yet. Okay. Because once we have this right here, what can we do to make this O minus neutral?
Oh, right.
We're done with the hard part, I would say. Well, actually, no. There's the second part that's kind of tricky.
Oh.
Can
halfway done. It?
Yes, protonate it. And what's the proton slice we can use to protonate it?
The H2O.
Yes, H2O, not H3O plus, not H2SO4. So don't just bring out a random H3O plus floating around anywhere. That you can't bring that out of nowhere. You gotta use what you have by either forming in the mechanism or using what you have in the reagent. Right? So this O minus here is gonna grab the H, kick out the OH to give us this intermediate here, the neutral OH, and this product here. And this product here is what we call an aldol. An aldehyde, and beta to the aldehyde is an alcohol. Aldol. Aldehyde next to alcohol. Aldol. Aldol. So this would be the final answer if we did not have heat, right? Like, if we didn't have heat, we stop here. Well, it's kind of iffy because different professors do it differently. Like, even though you don't have heat, professors just go and proceed with the reaction anyway as if they had heat. But for Levens, I think she follows it this way. I just have to see her notes when she goes over this reaction, Jenna, to see what she wants, right?
Okay.
This right here would be the intermediate because we have heat, so we're gonna keep going. We're gonna do aldol. That was aldol condensation, right? This process that we just did is aldol condensation. Aldol condensation. With heat, we're gonna do aldol dehydration, which is gonna get rid of a water molecule. Okay. Now, to think about the final product, we're gonna have something called an alpha, beta, unsaturated carbonyl. So right now it looks like a very long name, but we just have to break it down word by word, piece by piece to understand it. This right here is the carbonyl carbon. This right here is the alpha carbon, the first carbon away from the carbonyl carbon. Now we actually have two beta carbons, one beta carbon there and one beta carbon here. But we're interested in the beta carbon that is holding the alcohol. So I'm going to ignore that beta carbon right there because it's not attached to the alcohol. Right? Our final product here is going to get rid of the alcohol and put a double bond between the alpha and beta carbon. So it's going to look like this. Oh shit, no more alcohol. Right, alcohol is gone. But there's a double bond between this alpha carbon and the beta carbon that had the alcohol before. Right, so if we analyze the name, alpha carbon, beta carbon. double bond between the alpha and beta carbon. This double bond here is also considered as an unsaturation, right? Like unsaturated fat has double bonds, saturated fats has all single bonds, alkanes, right? And you're gonna see that more in biochem. But unsaturation, just think of that as a pi bond, like a double bond, a pi bond, or triple bond, or even a ring, right? And it's relative to the carbonyl, like the alpha and beta carbon relative to the carbonyl. So this right here is called an alpha beta unsaturated carbonyl. Okay, does that name make sense? Okay.
Yeah, I think so. So it's just like alpha is 1 carbon away from the carbonyl, beta is 2 carbons away from the carbonyl, but it could also depend, because we could say that to the left of the alpha is the beta, but why'd you say that's not true?
Yeah, so to the left of the alpha is also beta. That is true. Right? But because
we don't take that into account.
Yes, we don't take that into account because we're not interested in that beta carbon. We're more interested in this beta carbon here. Like this is still a beta carbon, right? It is still a beta carbon, but we're not interested in that beta carbon. We're interested in this beta carbon right here because it is attached to this hydroxyl group, alcohol group, right there. This beta carbon has no alcohol group.
What if there was no, like, is there a case where there's no alcohol group?
In this reaction, there would always be an alcohol group. There will always be an alcohol group.
Okay.
Right, for this reaction, yes.
Okay.
Other reactions, like with enolate ions, there could be a case with no alcohols, but that would not be aldol condensation anymore. That would be another reaction. Right. Because these reaction names here, like, don't get overwhelmed with a lot of reactions, because it's gonna like use the same nucleophile. Like this enolate ion here, where this is the alpha carbon nucleophile, it could attack a lot of electrophiles, right? It could attack an aldehyde, which is what we're doing right now for the aldol condensation and dehydration, or it could attack a primary halocane to do SN2, like that, right? So depending on what electrophile you have, it could give you a different reaction using the same nucleophile, like that, right? Just like think about it conceptually, like what's the chemistry of this enolate ion here. And the most important thing is that this enolate ion's nucleophile is this alpha carbon here. There's a negative charge on the alpha carbon, right? So our nucleophile is not the O- right there, like that. And we're gonna see more chemistry of this, which is I think I saw Levin's like started talking about the enolate chemistry at your most recent updated notes, Jenna, like with the alpha carbon acidity and then the enolate, right?
Yeah, it was very brief though. That's why I'm like kind of struggling with this stuff.
Yeah, conceptually, yeah, because it's a lot of conceptual stuff, like behind the scenes, what's going on. Like if you just do it, copy and paste, you know, like trying to memorize everything, then that is not very helpful on understanding and like applying it for the next reaction you learn, you know. But once you get the background information like this, you could like build on top of it and like you said, oh, that makes sense, makes sense. It's easier to pick up when you learn more reactions, new reactions, like that.
Yeah. Is this like one of the more complicated things in 8B?
You have to.
Or does it get worse?
In my opinion, I would say it gets worse with the carboxylic acid, derivatives, esters, amides, anhydrides. That's because that's 118C stuff. And then you're gonna like basically do 118C, a speed run without doing the spectroscopy, because there's also carbohydrates, sugars. Do you know those chair conformations with the like the axial equatorial things?
We literally did that in lab today.
That's gonna come back. Yeah.
Oh my god. I have such a terrible foundation in that stuff because I barely learned it last quarter.
Oh my gosh.
So I'm really scared.
Don't worry. I'll teach you what you need to know, and it's gonna be like, yeah, we're gonna do a lot of practice for you to be confident and build you up to speed.
Okay, that's
Don't worry.
good.
Yeah. Right. Okay.
Okay.
So the next thing here, right, is that we're gonna deprotonate the alpha hydrogen again with the OH minus. Right, this step here proceeds when we have heat. We're gonna generate the enolate ion again. Grab that alpha hydrogen, make a double bond between the alpha carbon and carbonyl carbon, push the double bond onto the oxygen, generating this enolate ion right here. Let me know when this did not make sense. Like, right here, from this molecule to this intermediate right here.
Okay, so we took the OH. We
Right. This
okay,
is
formed
just
the
a
double
base.
bond. Yeah. Okay, that makes sense.
Right. We form a double bond right here, which is this double bond, and then push the one onto the oxygen like that. Nice.
Yeah.
Okay. Now this is the irreversible step here, which is the last step. We're gonna reform the carbonyl by using one of its pairs of electrons on oxygen to make a double bond there, shift the double bond over here on that carbon, and kick out the OH minus. Like that. Okay, and that right there is an aldol dehydration reaction. Aldol dehydration. Reaction or mechanism, something like that. Because Lewis is very picky with the differences between the reaction and mechanism names. Right?
Yeah.
Dehydration. So, I should let's actually finish off with the vocab questions. The overall reaction 1A, like which is what we just did basically, is aldol dehydration reaction. That's what I would say.
Okay.
Aldol dehydration reaction. The reaction first forms an enolate ion, right, by deprotonating the alpha hydrogen. So the ion was already given. I'm just gonna draw what's in the blank right here. I'm just gonna write what's in the blank. Enolate ion, which is the nucleophile, specifically the alpha carbon of the enolate ion, which undergoes an mechanism. So
wait, no.
This is our enolate ion here, right, which undergoes a nucleophilic acyl addition mechanism.
Oh,
because
yeah.
This is our acyl group, the carbonyl group. But this nucleophile here is weird because you know how we're used to seeing a nucleophilic acyl addition with like CN minus, OH minus, OR minus, or amines.
Yeah.
From the imine. This nucleophile here is the enolate ion alpha carbon, which attacks an acyl group and pops it up there. Same mechanism like before, but it's a nucleophile this time. So it is a nucleophilic acyl mechanism. Nucleophilic acyl addition mechanism.
Yeah.
Okay, next one. Then with heating, the intermediate undergoes an aldol hydration reaction too. Aldol overall reaction is aldol. Oh, so
wait, isn't the first one condensation?
Yes, because I thought she said overall like towards the end, but aldol condensation is the first part of the mechanism, and with heat it goes to aldol dehydration.
Yeah.
Yeah. Wait. So I just realized that now because she wants aldol dehydration as the answer in the last blank, but I just realized that we already used the aldol dehydration. So I think she wants aldol condensation in the first reaction because it first goes through aldol condensation, and then with heat, it does aldol dehydration.
Because it does say overall reaction 1A. Wait, that whole thing is 1A.
Yeah, that whole thing is 1A.
Yeah.
Right, upside down. Because I thought she meant like overall, like up until the end, but she meant like up until like more general terms, like the aldol condensation reaction, which will eventually do dehydration at the end, right? Yeah, so I would change the first part of the question a little bit because it's kind of confusing with the overall ending part, but it's okay. It's okay. Yeah.
Yeah.
Yeah. Right, so these here should be your final answers, I think.
Okay. Yeah. Got it.
Okay.
That's it.
Good. Yes, that's it. Nice.
Yeah. Thank you.
Of course, Jenna.
Sorry I couldn't make it to office hours yesterday. I got home really late. I got home at like 9.
Oh, at 9. Oh my gosh. From the same spot, like the cafe you were staying at to study, or like the library?
Like I was studying that day, and I had to drive back here.
Oh, to Davis, right? To go back to school. And then it's pretty far.
Yeah, the drive is so annoying.
I know. But there was not that much traffic, right? Because you drove like late at night that time?
Yeah. I left at like 7, and we got home at like 8:40 something.
Okay, yeah, that's pretty good.
Yeah, but yeah, I wish I joined because I did have those questions, but
yeah,
I'll join tomorrow.
Yeah, definitely. It's good.
Yeah.
Okay.
Thank you.
Yeah. Good. Of course. Have a nice night, guys.
You too. Good night.
Good night.